Hello viewers, myself Dr. T. Oza. Today I am going to present to you a new video, very important one, very fundamental one. This is on chemical kinetics, basic principles. This video will be very helpful to you and easy to understand also. For clarity of the subject, the whole video will be discussed under these heads. Let us begin with the introduction. Chemistry is primarily a subject that studies chemical transformations, which a variety of reaction conditions or variables such as concentration of various chemical species present in the solution, the partial pressures of gaseous species, temperature, pH of the medium, dielectric constant, viscosity, intensity of radiations, ultrasonic frequency, time, and of course the type of species involved, including their physical states, particle size, surface area, polarity, etc. Whereas in chemical kinetics, we mainly focus on the rates of chemical changes, its feasibility, reversibility, non-feasibility, etc. That is energetics is discussed in thermodynamics. Thus, both chemical kinetics and thermodynamics are complementary branches, complementary to each other. As regards the rates of various reactions, some are immeasurably slow, some are slow, some are fast, and some others are very fast or instantaneous. Accordingly, a variety of analytical methods based on some suitable indicators have been employed to monitor the rates of reactions. Some methods employ traditional chemical analysis, potentiometry, polarimetry, colorimetry, etc., while some others are so fast that sophisticated methods like in situ spectrometry, particularly NMR and EPR, temperature jump method, and flash photolysis are used. For a better understanding of the step-by-step reaction mechanism, collateral data from thermodynamic measurements are absolutely necessary. So let us begin with the mathematical formulation of rate equations. In general, the rate of chemical reactions does not remain uniform throughout. Obviously, simple statistical methods would not suffice. We need to apply differential and integral calculus for a hypothetical chemical reaction, reactant A giving product P. Initial concentrations at time t equal to 0 are noted here. Then after the lapse of time t, reactant concentration falls, product concentration builds up. So you can formulate rate as R equal to minus dCA over dt. In this, dCA represents infinitesimally small amount of the reactant A. Likewise, dt means infinitesimally small time period. We can present rate either in terms of decreasing concentration of reactant or in terms of increasing concentration of product. Whichever is more suitable, more easy to measure, we can employ that method. For a more general case where two reactants A and B are involved, their moles are A and B, products are suppose L and M, their moles are L and M small. So the relative velocity can be written by equation number 1, noted here, and the rate can be written as R equal to Kn, Ca power P, Cv power Q. Here, Kn is called velocity constant of nth order reaction. P and Q are respective orders, means P is order with respect to reactant A, and Q is order with respect to reactant B. Sum of P and Q gives the whole order of the reaction. Now regarding velocity constant Kn, suppose concentration of both reactants are unity. In that case, velocity constant becomes equal to the rate. Order and molecularity of reaction. These are very important concepts. With reference to the equation 2 in the previous slide, P is the order with respect to reactant A, and similarly Q is the order with respect to reactant B. Overall order of the reaction is P plus Q. The order of a reaction cannot be read directly by looking at the balanced chemical equation. Instead, it is derived from the analysis of actual experimental data. Therefore, order can be 0, 1, 2, or 3, not more, or it could be fraction, half, 2.5, etc. Strangely, in some cases, the calculation shows order to be negative, although in very rare cases, but it does happen, particularly in biological reactions, which are very much sensitive to temperature. Molecularity is not so important term. It simply refers to the sum of the coefficient to each reactant in the balanced chemical equation. Molecularity has nothing to do with order. It is always a positive whole number. For example, for the reaction 2N2O5 giving 4NO2 and O2, molecularity is 2. Order of the reaction is 1. As I said earlier, order is derived from analysis of experimental data. Let us talk about experimental methods in kinetics. Depending on the nature of reaction under investigation, an appropriate method is chosen from over a dozen available techniques. For instance, a reaction involving one or more gaseous reactants or products. Measurement of pressure with respect to time is done. When chiral species are involved, polarimetry may become the easiest technique. Inversion of cane sugar, for example, is best followed polarimetrically. Cane sugar gives a picture of D-glucose and D-fructose in equal amount, and optical rotation changes during the reaction. So by measuring optical rotation as a function of time, the rate of this reaction can be followed. The other methods are based on measurement of electrical conductivity, spectrometry, volumetric titrations, gas chromatography, flow method, stopped flow method, pressure jump method, temperature jump method, NMR method, EPR method, etc., etc., etc. The study of very fast reactions, particularly biological processes, is done using chemistry. That is chemistry and the time scale 10 to the power minus 15 seconds. This is useful for the study of reactions involving very short-lived transient species as intermediates. Rate equations. First, we write differential rate equations. Then we integrate those equations to obtain practically useful equations. Here, a case of a hypothetical reaction has been listed. Reactant A giving product B. Initial concentrations are noted A at 0, A for reactant, 0 for product. Concentration after time T, A minus X for reactant, X for product. So we will now derive the equation assuming that this reaction belongs to first order category. So the rate becomes minus dCA over dt equal to K1CA. Minus sign because reactant concentration is decreasing. See, in this expression, left-hand side contains two variables, concentration and time, whereas the right-hand side has only concentration. So first we rearrange this equation. so that on both sides we have only one variable. Thereafter, we integrate the equation. On integration, we get minus ln C equal to K1T plus C. Here, C is an arbitrary constant called constant of integration. It can be evaluated by applying boundary conditions at time t equal to 0, x equal to 0. In that case, C becomes minus ln C0. Evaluation of constant we have done earlier. Now we substitute the value of C in equation 2. So we get minus ln Ct equal to K1T minus ln C0. We can transpose this equation to get ln C0 by Ct equal to K1T. From there, we derive K1 equal to 2.303 over T multiplied by log C0 by Ct. This equation can also be written in exponential form, sometimes called Wilmy equation. So equations 3 and 4 are of exponential forms. The more popular form is K1 equal to 1 over T multiplied by 2.303 multiplied by log of A over A minus X. Equation 5. So we can calculate K1 if we record concentrations at two different time intervals, T1 and T2. Then reactant concentration A minus X1 and A minus X2. We can obtain the so-called difference equation. Equation number 6 is difference equation. It involves two time limits, T2 and T1. Graphical display. If we plot time t, x-axis against log ct, y-axis, a straight line of slope minus k upon 2.3 should appear, and intercept equal to log c0. On the other hand, a plot between the reactant concentration, x-axis, and rate of reaction, y-axis, should give a straight line passing through the origin, slope equal to positive k, intercept equal to 0. Here, handwritten graphs are shown. The first graph is between concentration, Ca, vertical axis, time, horizontal axis. The second graph shows log of concentration, y-axis, and T, x-axis. In another diagram, we have shown rate along vertical axis and concentration along horizontal axis. In the last diagram, the concentration changes with time are shown for both reactant A and product B. Description of these graphs are given here as points A, B, C, and D. Now, test for first order reaction. How do we know that a reaction belongs to first order? For this, what we do, 3-4 sets of experimental kinetic data are gathered. Then they are calculated using first order equation. If rate constant remains the same, almost the same, then we can say that yes, the reaction belongs to first order. Similarly, for second order or third order, we can achieve the result. At least 3 or 4 sets of data are required. Each is analyzed, and if k becomes constant on particular equation, first order, second order, etc., then the end order is derived. Another method is graph can be plotted according to the particular equation. Then we take up some numerical problems. Numerical problem first. For hypothetical reaction 2A plus 3B given 1.5L plus 2M, the decrease in the concentration of A was found to be 0.03 mole per second. Now we have to calculate the rate of decrease of reactant B, rate of increase of reactant product L and rate of increase of product M. So we have to carry out a number of other calculations also noted here. First, we write comparative rates. Then we calculate very simple methods of calculating, clearly shown over here. Molecularity of the reaction is 2 plus 3 equal to 5. Regarding order, we write equation for order R1 equal to K, A power P, B power Q. This is first equation. Now, question says when concentration of A was doubled, order became twice of the R1 value. For that, equation number 2 is sufficient. Now, what we do, we determine R2 by R1, which is 2. So we put the relevant terms and we get 2 equal to 2 power P, which means P is 1. It means order with respect to A is 1. When the concentration of reactant B is changed, there occurs no effect on the rate of reaction. It means order with respect to B is 0. The overall order of the reaction is 1. Number 2 problem second. Some data are given for a reaction between NO gas and H2 gas. We have to find order, we have to find molecularity, and we have to guess the mechanism. We analyze the data. Molecularity is so simple to determine 2 plus 2 equal to 4. For order, we write equations for R1, R2, R3 and carry out simple division. It means R2 by R1 is 3 as given in the data. R3 by R1 is 12. R3 by R2 is 4. So we write the relevant equations. The values of two rates are given. From there, we derive R2 upon R1 equal to 3 equal to 3 power P, so that P is 1. Similarly, R3 upon R2 is 4. And when we put the data, question number 3 and 2, we get 4 equal to 4 raised to power Q. It means Q is 1. Evidently, order with respect to each reactant is 1 overall to second order case. Likewise, if order is known, we can calculate rate constant by using the equation K equal to R upon NO power Q, NO power P, H2 power Q. By putting the data, we have determined K value. Now, if K value is known for any given set of reactant concentration, we can determine the rate. In one case, we have assumed reactant concentration is 0.008 mole per liter. Then we have calculated the rate, which comes out to be 1.536 into 10 to the power minus 4 dm6 mole minus 2 second minus 1. Number problem 3. We have again considered a gas reaction N2O giving N2 and O2. So here a bit different approach will be followed. Order has been given as 1. So what we do, first we write the balanced equation. Number of moles at time t equal to 0, 1, 0, 0. Total moles 1. Initial pressure of N2O, Pi. At equilibrium, time is more than 0. Number of moles 1 minus x, x and x by 2. Total number of moles 1 plus x by 2. Now from this we can determine total pressure equal to Pn2O plus Pn2 plus PO2, Dalton's law of partial pressure. From this we can determine the value of x equal to 2 within bracket P minus Pi. P is total pressure, Pi is initial pressure of reactant. Because we have derived x, we can put the value of x And finally, we determine K1, equation for K1. K1 is equal to 1 upon T multiplied by natural log of Pi upon 3 Pi minus 2P. Problem number 4. Again, for the reaction A giving P, the reaction says after 40.5 minutes, 25% of A got decomposed. It means 75% remains. We have to derive the rate expression and calculate the first order rate constant K1. Solution. Write the rate equation as we did earlier. Carry out separation of variables and integrate. We get minus ln C equal to K1T plus C. Evaluate the integration constant C as before, and we derive the Wilmy equation Ct equal to C0 multiplied by e raised power minus K1T. And K1 has been determined as 7.11 into 10 to the power minus 3 per minute. Problem number 5. We have to find the ratio for 99.9% to 50% completion of a first order reaction A to P. So we write equation for T. T is K inverse multiplied by natural log C0 by Ct. For T 50%, we write the equation. Accordingly, for T 99.9%, we write the equation. Then we divide second equation by first equation and we get 10. It means 50% completion time will have to be multiplied by 10. 10 times more time is required. Number 2, problem 6 is based on the earlier question. The virus load is reduced by 50% by first washing your hands with soap and water. How many consecutive washings would be needed for bringing down the virus load to less than 0.1%? The solution says 10 times. If you wash your hands 10 times, then the virus load will be reduced to the 0.1%. Units of Kn, very important thing. We have to determine the units of K1. The general method is Kn equal to mole power 1 minus n, liter power n minus 1, and T power minus 1. So for zero order, first order, second order, 2.5 order, 1.5 order, third order, we have determined the unit of K. Now we go on to second order reactions. First, we take up a reaction in which only one reactant is involved, A equal to P. This case is very simple. Initial concentrations are given, A and 0. Other concentrations are A minus X and X. And the rate expression can be written dx by dt equal to K2 A minus X power 2. It can be rearranged and integrated, and on integration we get 1 upon A minus X equal to K2 T plus C. C is the integration constant. It can be evaluated by applying boundary conditions. By rearranging, we get the final equation K2 equal to X over AT multiplied by A minus X. Then we take up second type reaction in which two reactants are involved, both having unequal concentrations. This is a bit tricky. Here in this case, we have to apply fractional method. What we do, first we write rate expression dx by dt equal to K2 A minus X B minus X. Then we transpose it, dx over A minus X B minus X equal to K2 dt. We first write 1 over A minus X B minus X equal to A upon A minus X plus B upon B minus X. Here in this case, A and B are arbitrary constants. We will determine their values later. Now we have to determine A and B by applying limiting conditions. When x is A, then we derive A equal to 1 upon B minus A. When x is B, we derive B equal to A upon A minus B. Now we put these values, and now the integration becomes very simple. On integration and rearranging, we get 1 upon A minus B, ln B minus x over B minus x equal to K2 T plus C. C can be evaluated by applying boundary conditions, putting the value of C and rearranging. Finally, we get K2 equal to 1 upon T A minus B into ln B A minus x over A B minus x. This equation results assuming A is greater than B. If A is less than B, then equation 4 is valid. One more important thing, in this equation, this is a straight line equation following y equal to mx plus c rule. Here variable y means 1 over A minus B into ln B A minus x on A B minus x. Variable x equal to t and slope equal to m. K2 equal intersect is 0. And here K2 is m, slope. So by plotting graph, slope can be determined. Thank you very much. Thank you. I hope if you read it carefully, you can be benefited. And the topic is very, very important. I have covered only basic facts, not detailed ones. In later videos, we shall be covering some other aspects also. Thank you very much.